nice slides. I'm really ticked off that that's not working. So, anywho, this right here demonstrates the wave nature of light because of the way things interact. And if we're not going to do the experiment on Tuesday on this, then I will bring in on Tuesday in the lecture a laser and set the thing up for you here as an in-class demonstration. I want you guys to see it because this was the experiment that kind of got me into physics. I mean, it did. I was always mechanically minded, but when I saw this, I thought this was really, really amazing because suddenly light, the stuff that we see, we used to see every day, it's ubiquitous, it's all over, every aspect of our lives. Now we're looking at it so closely that we're seeing it's actually a wave and it interacts with itself, and there's all sorts of neat things you can do with it because it's a wave. Yeah.
Is that like somewhat analogous to like two people jumping on a trampoline, and like the closer they are together, if you can like, I don't know if you've ever jumped on a trampoline before with somebody else, you can like bounce them up higher the closer you are together. If you like do it at the right time, right before they hit the trampoline.
That has a lot to do with phase. Yeah, you got to be in phase to assist. And if you and your partner on the trampoline are out of phase with each other, things don't work very well, right? You kind of cancel each other's efforts out.
It always be so disappointing because you think they're about to like pop you up.
Yeah.
They do it wrong.
And then your knees are both down.
Yeah.
That's all I could think about this entire time. Trampoline.
I had to do that.
So here's something I can do. I can actually add a whole bunch of slits. And instead of just two, why just two? Why not make a lot? Why not make a million? And let's space them really closely together. And what we do, when we do something like this, and we make lots and lots and lots of slits. And instead of water passing through, we're not talking about light passing through all this, and it's all constructively and destructively interfering. The more slits we add and the more tightly we compact them together, the more destructive interference dominates, and you have a little bit of constructive interference that happens. And this is what we call a diffraction grating. So a diffraction grating is just a piece of glass that has very, very fine scratches in it that act as blocks to the light. They can't. If you had a sandblasted window, you can't shine light clearly through it. Most of it comes back at you. But if you were to take, let's say we were to take that glass pane right there and put tape on it, and leave ourselves little tiny stripes, okay? And we sandblast over this strong tape. The exposed parts get sandblasted, and then we pull the tape off, and we've got clear strips, okay? That's the kind of thing that a diffraction grating is, except diffraction gratings are kind of amazing. I guess they use a diamond to scratch these things so fun that they put like 3,200 scratches per centimeter. So it's really, if you look at it, it looks like a piece of glass. You can't even really, there's something weird about it because there's a little bit of an odd optical look to them, but they look almost like a regular piece of glass. The scratches are so fine and they're so close together. But what it does is it produces a couple well-placed constructive interference spots. So I thought I would give you an application of this principle of the wave nature of light. If you take a CD and you look at it under a microscope, you will see little dots, little raised bumps, dimples or something. And when you put a CD or a DVD into your player, this laser is what is supposedly reading the dots and converting that into digital information, and then you're watching SpongeBob and Michelle's games. Nice. Thanks. Okay. That was totally unprepared. All right, let me get rid of some of this, and I'll show you what a CD player does, because I think this is cool. And I think you will too. You'll never look at a CD the same way again. We're going going to look at a cross-section of the CD. So our CD is, we're looking at the edge, and maybe we're taking just a slice of it. We see that there are bumps. There might be a bump here, and then on the next track, there's a bump here, and a bump here, and here's the center of the thing. So you got all these bumps. It's kind of like a record player, really. And what we want to do is we want to have laser light come down, and when it hits a bump, the laser light just goes all over the place. When the bump is no longer in place, when this thing is rotating, we move this thing, we're rotating it like this, we get to a place where there's no bump. And suddenly, the light hits this nice, shiny surface and reflects back. In fact, what we need to do is not make this straight down. Let's just do this. Let's make it a little bit of an angle. Angle of incidence. Okay? It hits this nice, shiny surface, and it reflects. And the angle of incidence is equal to the angle of reflection, right? So it reflects. Oops. Right. There we go. Angle of reflection. And what are we going to have? We're going to have right here a detector. The detector is getting this strobe of little pulses of light, because when the next bump shows up, this reflected light just goes somewhere crazy. It doesn't get to the detector. You know, the bump is causing an interference. It's just sending the light in crazy ways. Okay? It's only when there's not a bump that it gets to the detector, and the detector measures that little burst of energy and says, ah, that's a 1. And then it turns off, it's like 0, 1, 0, 1, 0, and it's doing this binary code kind of thing. Okay? So that's what's going on. And it just goes along and scroll. You know, if you look at the CD as a circle, you've got all the bumps like this. And I'm going to exaggerate how it works. But it corkscrews, actually it corkscrews outward, I think, but it doesn't matter. It's going along a spiral path either way, in or out. So let's say it does this. So it's going 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. There's the end, there's the credits, you're done. Okay? How does it know where to read? I mean, with a record player, the needle resided in the groove. It was kind of in there, stuck, and it was being dragged along the groove. And of course, if you had a scratch on the record, it would hop over and it would ruin your, you wouldn't be able to listen to it. It'd be like listening to some record and it would just skip over. Okay? Well, how does it keep from skipping? What's tracking this thing? Turns out it's a diffraction grating. If anybody was going to guess that, you should have. Yeah, leading up to this diffraction grating, right? So here's what we're going to do. We are going to put a diffraction grating in here. It's just a little, so here's the laser. And we're going to put a diffraction grating, which is a little plate. And the diffraction grating is this scenario over here with lots and lots of little scratches. And most of what happens is destructive interference. And so what we're going to say is we get a central bright fringe and 2 neighboring bright fringes, and that's it. Okay? So here's our laser light that goes through the diffraction grating, and because we're talking about this symmetric line, it's bright. Okay? You get this bright fringe taking place here. But then we have to go a certain distance away to get to our next bright fringe. And so we get secondaries. We get what amounts to this and this. Okay? So what this looks like is, here's our little plot. We've got this scenario. That's our diffraction grating. There's a primary that goes to the detector and tells us what the information is. And we've got these 2 guys that come in, and they are always in between rows of dots. They're always on a shiny surface, and they're always coming in at a particular angle. This one comes in, and I'm going to have to use a different color. So this one hops over here, and there's another little mini detector for tracking. And here's another detector over here, also for tracking. So if this laser starts to wander off track, what happens is, let's say it starts to wander this way. This laser light is going to start to hit the bumps. And once it hits the bumps, it goes crazy. This detector loses its signal, right? The light never makes it. If it hits here, it goes like that. This guy said, uh-oh, lost the signal. Tells the motor to move back this way. If this thing starts to slide this way too much, there'll be a bump over here that this one will interfere with, right here, and it'll say, oh, I lost the signal to that one, and it'll start to track back. And that's how it stays on track. So you want one more application on the CD player? You know CDs aren't just a piece of metal foil. They've got plastic coating on them, don't they? Transparent coating to keep, somewhat for protection of the information. You can toss CDs around; they're pretty durable. So what we do is we can talk about this. Well, this whole thing is encapsulated in some plastic. Yeah. The index of refraction of plastic is different than air. Ooh, what happens when you talk about different index of refractions? Say the law. Snell's law. Yeah. So now we don't have just a straight shot in. We have an angle of refraction, an angle of reflection on this surface, and then it refracts back out into air. And so we have to make sure a placement of detectors accounts for that. It doesn't change the physics of how the CD player operates, but it does change the location of the detectors. So you have to know the thickness of the plastic of the CD. That's why you don't see various thicknesses of CDs. They're all the same. So here's one more tiny little bit of information, and then you're done. This was red light. What kind of players are you typically buying CDs from? Blu-ray. You know why they call it Blu-ray? They use a blue laser. Why do they use a blue laser? Huh?
Shorter
It's pretty.
It's shorter wave.
It's a shorter wavelength, and so because it's a shorter wavelength, we can run through a diffraction grating and get a narrower band. Well, first of all, we can space these guys closer together, so we can put more dots in between. Red light has a big wavelength, and so you can only resolve bumps that are bigger than the wait. Okay, so if you've got a wavelength that's really big, like if you're, here we go, microscope. AV biology folks, you try to look through a microscope and see a cell, no problem. You can see a cell. Can you see the organelles? Sure. Can you believe that I knew what an organelle was? I don't really. But I can look, so I'm looking at this thing, I can see that, but can I see the DNA? No, I can't see the DNA.